Hello and welcome to the lecture session on series solution of Legendre Differential equation. Power series. Consider the ordinary differential equation in the form P0 of x y double dash plus P1 of x y dash plus P2 of x y is 0. Call this as equation number 1, where P0 of x, P1 of x and P2 of x are polynomials in x with P0 of x not equals to 0 at x equals to 0. So we will assume the solution to be in the form of y is ar x power r, where r is 0 to infinity. And when we put r is equals to 0 to infinity, we will be getting a0 plus a1x plus a2x square and so on. Instead of writing, we can write it in the simplest form, that is a summation. And since it is required in the differential equation, we can observe in the previous slide, y is required, y double dash and y dash also is required in the first equation in order to substitute to get the solution. So y is assumed in this form, and let's obtain what is y dash and y double dash. If we differentiate this one, ar into r x to the power of r minus 1 and y double dash is equals to ar into r minus 1 into x power r minus 2. These are the three equations or three values we will be getting for y dash and y double dash. These can be substituted in the equation 1. So equate the coefficients of various powers of x to 0. In general, when the coefficients of x to the power of r is equated to 0, we obtain a recurrence relation which will help us to determine the constants a2, a3, etc. in terms of a0 and a1. Substitute all these values in y is equals to, which when we expand it, we will get it as a0, a1x plus etc., which we have assumed it in the summation form earlier. Thus, the power series solution of the ODE in the form y is a0 f of x plus a1 g of x, where f of x and g of x are convergent infinite series in x. Series solution of the Legendre differential equation is given by 1 minus x square y double dash minus 2x y dash plus n plus 1y is equals to 0. Call this as equation number 1. The coefficient of y double dash is p0 of x, which can be written as 1 minus x square, and p0 of x is not 0 at x is equals to 0. Therefore, we apply the power series method. Let us take y is equals to ar x power r, y dash is ar r x power r x minus r into x power r minus 1, y double dash is ar r x power r minus 1 x power r minus 2. That is on differentiation with respect to x one time and two times. So substituting y dash and y double dash in the equation 1, we get 1 minus x square into ar r minus 1 x power r minus 2 minus 2x times of ar r x power r minus 1 plus n plus 1 into summation ar into x power r, that is equals to 0. Now we will take this 1 minus x square in the previous equation to inside the summation, or we are multiplying it. Then what happens? The first term will be ar into r minus 1 x power r minus 2 minus, when we multiply x square to x to the power of r minus 2, it becomes x power r only, and it is ar minus 1 into x power r minus 2 times of, again x is multiplied to x power r minus 1, it becomes x power r. So it is 2ar into r x power r plus n plus 1 into sigma ar x power r is equals to 0. This is on substitution of y dash and y double dash, and then simplifying and adding the power of the like terms. Equate the coefficient of x to 0, that is, coefficient of x power minus 2 will be a naught into 0 into minus 1, that is equated to 0, where a naught is not equals to 0. Coefficient of x power minus 1, that is a1, 1, 0 is equated to 0, and a1 is not equals to 0. Coefficient of x power r, that is ar plus 2, r plus 2, r plus 1 minus ar into r minus 1 minus 2ar into r plus n plus 1 into ar is equals to 0. So, after taking everything to the right hand side and simplification, what do we get is ar plus 2 is equals to minus of n plus 1 minus r square minus r. By taking the ar outside, it is divided by r plus 1 into r plus 2, we get it. Put r is equals to 0, 1, 2, 3, etc. We get a2 as minus n plus 1 by 2 into a naught, a3 as minus n minus 1 n plus 2 by 6 of a1, and a4 like this with the a naught, and a5 again n minus 1 into n plus 2 n minus 3 into n plus 4 into a1 divided by 120 and so on. Actually, this 24 and all this is we can write it as the respective factorials. See, a2 is nothing but in the denominator of the right hand side it is 2. We can write it as 2 factorial. a3 and in the right hand side the denominator is 6. So we can write it as 3 factorial. And similarly for a4, the right hand side 24 can be also written as 4 factorial, and a5 120 is 5 factorial and so on. Substitute these in y. So we are getting y is equals to a naught plus a1x plus a2x square plus etc. That is anyway a naught is sum for terms, that is for even terms it is a naught is common, and for odd terms a1 is common. Let us substitute, group it as a naught terms separately and a1 terms separately. So we are getting a naught into 1 minus n plus 1 by 2 factorial x square plus n plus 1 n minus 2 and n plus 3 by 4 factorial into x power 4 and so on. Similarly, the odd terms, that is a1 is multiplied with x minus of n minus 1 n plus 2 divided by 3 factorial into x cube plus n minus 1 n plus 2 n minus 3 n plus 4 into x power 4 by 5 factorial and so on. How do we remember these terms? When it is multiplied with a naught, that is an even term, all for the negative terms it is n minus 2, n minus 4 like that we will get it. And all the denominators we can observe, it is for the first term it is divided by 0 factorial, and for the second term 2 factorial, 4 factorial and so on. Whereas when it comes to a1, for the first term it is divided by 1 factorial, and for the second term 3 factorial, and third term is 5 factorial and so on. And we can also observe one thing, two terms will be there, that is one is n minus 1, other one is n plus 2. So for the odd terms we'll have a negative sign. That also one of the hint I could like to give. Next, y is given by a naught into u of x plus a1 into v of x, where u of x and v of x are infinite series. This is the series solution of Legendre differential equation. Thank you. Any doubts? You can get back.